Welcome to Lecture 8, Continuity, Section 3.1 of the text Advanced Calculus by Patrick M. Fitzpatrick. This is Dr. Gilbert, Eyabi. In Chapter 2, we considered real-valued functions that have as their domains the set of natural numbers, and those were sequences. We now begin the study of real-valued functions having as their domains a general subset of the set of real numbers R. The standard notation for the domain would be D, so we would consider the function f from D to R. D is the domain and R is the co-domain. So what we are saying is that for every x in D, f of x is the value that the function f assigns to x. Now, two of the concepts essential to an analytic description of functions f from D to R are continuity and differentiability. So in Chapter 3, we would cover the continuity of a function at a point x0 in D and also the continuity of a function on the entire domain. And in Chapter 4, we would deal with differentiability. Subsection 3.1.1 definition. This is the definition of continuity at a point x0. I personally call this the sequential definition of continuity at a point x0. The reason why I call it a sequential definition of continuity is because further in this chapter we would learn the epsilon delta definition of continuity at a point x0. So if I ask you to give me the sequential definition of continuity, this is the definition I expect from you. A function f from a domain D to the set of real numbers is said to be continuous at a point x0 in D, provided that whenever the sequence xn in D converges to x0, then the image sequence f of xn converges to f of x0. If f from D to R is continuous at every point in D, then we say f is continuous on the entire domain D. I.e., what we are saying is if x0 is a point in D, then f from D to R is continuous at the point x0 if whenever the sequence xn converges to x0, f of xn converges to f of x0, i.e., if the limit as n approaches infinity of xn equals x0, then we would expect the limit as x approaches infinity of f of xn to be f of x0. So to prove that a function f is continuous at any given point x0 in a domain, we would start by saying, suppose the limit as n approaches infinity of xn equals x0. Then we would go ahead and prove that the limit as n approaches infinity of f of xn equals f of x0. If that happens, then we can conclude that the function f is continuous at the point x0. Or we can further revise this as whenever the limit as n approaches infinity of xn minus x0 equals 0, then the limit as n approaches infinity of f of xn minus f of x0 equals 0. Okay, if that happens, we say f is continuous at the point x0. Again, if f is continuous at x0 for every x0 in D, then f is continuous on the entire domain D. So if I ask you to prove that f is continuous on a domain D, all you have to do is let x0 be an arbitrary point on the domain, prove that f is continuous at that point. Let's look at some examples. Example 1. Define f to be a function from R to R by f of x equals x squared minus 2x plus 4. This is a polynomial function. As we would see later, polynomial functions are continuous on R. Okay, let's prove that f is continuous on R. So what we do is we pick an x0 in R and prove that f is continuous at the point x0. Again, what is our procedure? Suppose xn is a sequence in R such that xn converges to x0. We must show that the sequence f of xn converges to f of x0. But the sequence xn converges to x0 simply means the limit as n approaches infinity of xn equals x0. So we have to investigate the limit as n approaches infinity of f of xn and see where that leads. So limit as n approaches infinity of f of xn equals the limit as n approaches infinity. Wherever you see x, you replace that with xn. So that is limit as n approaches infinity. This is our function f right here. So everywhere you see x, you replace that with xn. And that becomes xn squared minus 2xn plus 4. And that equals, by the product limit theorem, by the sum limit theorem, by the constant multiple limit theorem. So basically what we're doing is, by the sum limit theorem, we can distribute limit across subtraction and addition. By product limit theorem, we can distribute our limit right here on xn squared. And by the constant multiple limit theorem, I can pull my 2 out and I have limit as n approaches infinity of xn. So we have, by the product limit theorem, by the sum limit theorem, by the constant multiple limit theorem, this would equal limit as n approaches infinity of xn, all of that squared, minus 2 times limit as n approaches infinity of xn plus 4. 4 is a constant, so it just stays as 4. And since xn converges to x naught, this will be x naught squared minus 2x naught plus 4, because the limit as n approaches infinity of xn is x naught. But x naught squared minus 2x naught plus 4 is simply f of x naught from the definition of f. So we have shown that whenever xn converges to x naught, f of xn converges to f of x naught. Thus, f is continuous at the point x naught in R. Since x naught was chosen at random or arbitrarily, we can conclude that f is continuous on the domain R. As a matter of fact, polynomial functions are continuous on R. Example 2. Define the function f from the set of real numbers to the set of real numbers by f of x equals 1 if x is greater than or equal to 0, and f of x equals 2 if x is less than 0. So if x is greater than or equal to 0, we have a constant function, f of x equals 1. And if it is less than 0, then it is a constant function, f of x equals 2. But we have a problem with the point x equals 0. Prove that f is continuous everywhere except at the point x naught equals 0. So this is an example of a function that is continuous everywhere except at a particular point. Our first example was a function that was continuous everywhere on the set of real numbers. Our second example is a function that is continuous everywhere except at some point. And we shall look at the third example, which would be a function that is nowhere continuous at all. So let's go ahead and prove this. Proof. We would first prove that f is not continuous at the point x naught equals 0, and then we would proceed to show that when x is not 0, then f of x is a constant function, and constant functions are continuous. By the way, I should just mention that we can loosely define a continuous function as a function whose graph can be drawn with a pencil on a paper without lifting up your hand. So a constant function, you can draw the graph of a constant function without lifting up your pencil. So that would be continuous, but we are going to prove it more rigorously. To prove that f is not continuous at 0, what we would do is find a sequence xn that converges to 0 and show that f of xn does not converge to f of 0. So let's try that. Consider the sequence negative 1 over n. Then limit as n approaches infinity of negative 1 over n is 0. Let's now investigate the limit as n approaches infinity of f of negative 1 over n. That equals limit as n approaches infinity of 2. Negative 1 over n is less than 0, and by the definition of f of x equals 2 whenever x is less than 0. So that equals limit as n approaches infinity of 2, which is 2 because 2 is just a constant, but f of 0 is 1. By our definition, when x equals 0, f of x is 1. So we have limit as n approaches infinity of f of negative 1 over n equals 2, which is different from f of 0, which is 1. So we can conclude that f is not continuous at the point x0 equals 0. Secondly, we consider the case when x0 is different from 0 and prove that f would be continuous. Suppose x0 is an arbitrary point on the set of real numbers that's different from 0, and suppose xn converges to x0. Then that means I can find a natural number n, uppercase N, such that f of xn equals f of x0 for every n greater than or equal to n. But that simply means the limit as n approaches infinity of f of xn equals f of x0. So by the definition of continuity, precisely the sequential definition of continuity, we can conclude that f is continuous at the point x0. As a matter of fact, whenever x0 is different from 0, f is a constant function, and all constant functions are continuous. But what we have up here is a more rigorous proof of the fact that f is continuous at every point except at the point x0 equals 0. And that is example 2. We will proceed to example 3 to show that there is actually a function that is nowhere continuous. And it is an exciting example. It is called the Dirichlet's function. So define the function f from r to r by f of x equals 1 if x is a rational number, 0 if x is an irrational number. Do not forget that both the set of rational numbers q and the set of irrational numbers qc are dense in R. So it doesn't matter how small an interval is, I can always find a rational number in that interval. I can find an irrational number in that interval. As a matter of fact, there is nothing as two consecutive real numbers being both rational. One has to be rational, one has to be irrational. In fact, we cannot even talk of two consecutive real numbers because there are infinitely many real numbers between any two given real numbers. So this is an interesting example. If you were to graph this, it will be impossible. It will be 1 0 1 0 1 0 1 0 1 0 1 0, and because there are infinitely many real numbers between any two real numbers, there is just no way you can even graph this at all. So the whole idea of lifting up the pencil from the paper doesn't even hold here because you just cannot graph this. It's impossible. So this is called the Dirichlet's function. We want to prove that the Dirichlet's function is nowhere continuous, i.e. there is no x0 such that our function would be continuous. Interesting. So how are we going to do this? We have to show that if I pick an x0 at random and find a sequence that converges to x0, f of that sequence cannot converge to f of x0. Let's go ahead and show you how we do that. Let x0 be a real number. By the sequential density of q and qc, set of rational numbers and irrational numbers, there exists an irrational sequence Vn such that Vn converges to x0. Recall the definition of a set S being sequentially dense. It means for every real number x, I can always find a sequence from S that converges to x. Okay, so because Q and QC are both dense in R, and x0 is a point in R, I can find a sequence of irrational numbers that converges to x0, and I can also find a sequence of rational numbers un that converges to x0. Now, un is a sequence of rational numbers, so by my definition of f of un will be 1. Vn is a sequence of irrational numbers, so f of Vn would be 0. So right here, I have f of un equals 1 because un is a sequence of rational numbers, and f of Vn equals 0 because Vn is a sequence of irrational numbers. So the limit as n approaches infinity of f of un would be equal to 1. F of un is 1. And the limit as n approaches infinity of f of Vn will be equal to 0. Since both of the sequences Un and Vn converge to x0, it is not possible for f to be continuous at x0, because we would have expected that f of Un would converge to f of x0 and f of Vn would converge to f of x0. But we see there that they both converge to different points, 1 and 0, which are different. And x0 cannot be 1, and f of x0 cannot be 1 and be 0 at the same time. So we can conclude that f is not continuous at x0. And since x0 was chosen arbitrarily on the set of real numbers, we can say that f is nowhere continuous. Now also observe that one expression of the discontinuous nature of the Dirichlet function is what I've mentioned before. There is no way to graph the function because there are infinitely many real numbers between any two given real numbers, and Q and QC are dense in R. So this is an example of a function that is nowhere continuous. So we have seen an example of a function that is continuous everywhere on the set of real numbers, an example of a function that is continuous everywhere except at a given point, an example of a function that is nowhere continuous. I need you to start generating your own examples. If I ask you in the test to generate for me an example of a function that is continuous everywhere except at the point 6, you should be able to do that. If I ask you to give me another example of a function that is nowhere continuous, you should be able to use the idea of the Dirichlet function to generate yours. So get to work. Subsection 3.1.2 definition. Let f be a function from D to R. Again, D is the domain. G a function from D to R. So f and G have the same domains. We define f plus g and f times g as f plus g of x equals f of x plus g of x, and f times g of x equals f of x times g of x for every x in the domain D. Observe that here we are dealing with multiplication. This is not composition, which we would see later. And furthermore, if g of x is different from 0 for every x in D, then f divided by g of x is f of x divided by g of x for every x in the domain D. So for example, if f of x is our function 2x squared plus 1, and g of x is our function negative x squared plus 3x minus 1, then f plus g of x will be f of x plus g of x, which would be adding these two functions. F g of x would be f of x times g of x, which would be multiplying these two functions, and f divided by g of x would be f of x divided by g of x, and I will have the quotient of these two functions. Now let's look at the main theorem of this section. Subsection 3.1.3 theorem. Suppose f and g, both having the same domains, are continuous at the point x0, then f plus g is continuous, f times g is continuous, and f divided by g is continuous at x0, provided that g of x is different from 0 for every x in our domain D. In other words, the sum of continuous functions is continuous, the product of continuous functions is continuous, and the quotient of continuous functions is continuous. Let's go ahead and prove that. Suppose f and g are continuous at the point x0. I want to prove that their sum, product, and quotient are also continuous. G of x is different from 0 for every x in the domain D. Again, what is our procedure? Suppose the limit as n approaches infinity of the sequence xn is 0. I have to show that the limit as n approaches infinity of f plus g of xn equals f plus g of x0. Well, by definition, that equals limit as n approaches infinity of f of xn plus g of xn, and by the sum limit theorem, I break this down as the limit as n approaches infinity of f of xn plus the limit as n approaches infinity of g of xn. But f and g are both continuous at the point x0. Therefore, the limit as n approaches infinity of f of xn is f of x0, and the limit as n approaches infinity of g of xn is g of x0. Again, by definition of addition, this will be f plus g of x naught. So we have shown that f plus g of xn converges to f plus g of x naught, and therefore we can conclude that the function f plus g is continuous at the point x naught. Beautiful. Secondly, limit as n approaches infinity, f of xn times g of xn, and by the product limit theorem, that is limit as n approaches infinity of f of xn times the limit as n approaches infinity of g of xn. But f and g are continuous at the point x naught, so this gives us f of x naught, and this gives us g of x naught, and by definition, that will be fg of x naught. Therefore, we can conclude that fg is also continuous at x naught in D. And finally, the quotient. Limit as n approaches infinity of f divided by g of xn is by definition limit as n approaches infinity of f of xn divided by g of xn. And here we're saying that g of xn is different from 0 for every n in n. And by the quotient limit theorem, I can split that up. And that equals f of x naught divided by g of x naught, because f and g are continuous at x naught. And again, by definition, that is f divided by g of x naught. Therefore, we can conclude that f divided by g is continuous at x naught. The sum, product, quotient of continuous functions would be continuous. As a matter of fact, even the composition of continuous functions is continuous. And that is the last theorem we would see in this section. But before we get there, let's take a corollary. Let P from R to R and Q from R to R be polynomials. Then the quotient P over Q from a domain D to R is continuous, where D is defined as the set of all x such that Q of x is different from 0. And the proof of this follows directly from Theorem 3.1.3. And now we get to the last theorem of this section, and we start off with a definition. Subsection 3.1.5 definition. Let f be a function from the domain D to the set of real numbers R, and G from U to R such that f of D is a subset of U. Then we can define the composition of functions f and g denoted by g composed with f as starting from the domain D and going to R. So look at this picture right here. F is a mapping from D to R, but since f of D is contained in U, we can view f as a mapping from D to U. U is a subset of R, and G is a mapping from U to R. So we can link this chain up and we would have a mapping from D straight to R, and this is called G composed with F from D to R, or GUF. So to evaluate this function, we would evaluate F first and then G next. So G composed with F of X is G of F of X for every X in D. Now we have the theorem. Subsection 3.1.6 theorem. For functions f from D to R, g from U to R such that f of D is contained in U, suppose that f is continuous at x naught in D, and g is continuous at f of x naught in U, then the composition g composed with f is continuous at the point x naught. So f is continuous at x naught, g is continuous at f of x naught, and g composed with f would be continuous at x naught. Let's go ahead and prove that. Proof. Let xn be a sequence in D that converges to the point x naught. By the continuity of the function f from D to R at the point x naught, the sequence f of xn converges to f of x naught. But we know that f of D is a subset of U. So the sequence f of xn is a sequence in U, and that sequence converges to f of x naught. So by the continuity of g from U to R, our sequence g of f of xn would have to converge to g of f of x naught, i.e. we're saying that the limit as n approaches infinity of g composed with f of xn would be G composed with F of X naught. In other words, the composition G composed with F is continuous at X naught. And in general, we would say that the composition of continuous functions is continuous. This brings us to the end of section 3.1, and in subsequent sections, we would investigate uniform continuity, epsilon delta definition of continuity, epsilon delta definition of uniform continuity, the mean value theorem, and so on and so forth. Thank you, and God bless you, and I'll see you in lecture 9.